Engineering applications. Efficiency. In Chapter 7, we noted that the second law of thermodynamics led to concept of thermal efficiency for a heat engine where where W net is the network of the cycle and QH is the heat transfer from high temperature reservoir. In this chapter, we have extended our application of the second law to control volume process. And in the previous section, we considered several different types of devices for a steady-state process. These include an ideal turbine, compressor, and nozzle. We realized that actual devices of this type are not reversible, but the reversible model may in fact be very useful to compare with evaluate the real irreversible devices in making engineering calculations. This leads in each type of device to a component of machine process efficiency. For example, we might be interested in the efficiency of a turbine in a steam power plant or of the compressor in a gas turbine engine. In general, we can say that determine the efficiency of machine in which a process takes place. We compare the actual performance of the machine under given condition to the performance that would have been achieved in the ideal process. So we can take a note that to determine the efficiency of a machine, in which a process takes place, we compare the actual performance of the machine under given condition to the performance that would have been achieved in an ideal process. It is in the definition of this ideal process that the second law becomes a major consideration. For example, a steam turbine is intended to be an adiabatic machine. The only heat transfer is unavoidable heat transfer that takes place between the given turbine and the surrounding. We also know that for a given turbine steam operating in a steady-state manner, the state of the steam entering the turbine and the exhaust pressure are fixed. For a turbine, steam turbine, the exhaust pressure and the state of the and the exhaust pressure are fixed. In other words, the variable P, I, T, I, and Pe are the design variable for turbine. Pi, Ti, and Pe are the design variables. The first two because the working fluid has been prepared in prior process to be at this condition at the turbine inlet, while the exit pressure is fixed by the environmental into which the turbine exhausts. Thus, the ideal turbine processes would go from state I to state E as shown in the picture here. Point I and point E. For the ideal process, we go from I to ES. For example, it is ideal process. And also on the PV diagram, we have the I point and also ES, ideal process, real process, shown in the picture. Whereas the real turbine is irreversible with the exhaust at the larger entropy at the real exit state E. This figure also shows typically state for a steam turbine, where state ES is the two-phase region, and state E may be as well as or may be the superheated vapor region depending on the extent of irreversibility of the real process. Denoting the work done in the real process I to E as W and the down in the ideal isentropic process from Pi Ti to Pe and Ws We define efficiency of the turbine as this relation. Hi minus H E Hi minus HES. Real work, ideal process work. The same definition applies to gas turbine where all states are in the gaseous phase. Typical turbine efficiency are with large turbines usually having higher efficiency than small. It is important to keep in mind that the turbine efficiency is defined in terms of an ideal isentropic process from PI/TI to PE even when one or more of these variables is unknown. There is various examples related to this topic as we discussed previously. Unless specifically noted to the contrary, we normally assume compressors or pumps to be adiabatic. We normally assume compressor or pump to be adiabatic. In this case, the fluids enters the compressors EI, TI, and the condition at which it exists, and PE, the reason for building the compressor. Thus, the ideal process between the given inlet states and the exit pressure would be an isentropic process between I and state E. For an ideal process, we have isentropic process for pumps, turbines, and compressors. The real process, however, is irreversible. And the fluid exists at the real state E with a larger entropy, and a larger amount of work input W is required. The compressor efficiency is defined as Typical compressor efficiency are with large compressor usually having higher efficiency than a small one. If an effort is made to cool a gas during compression by using a water jacket or freeze, the ideal process is considered reversible thermal process. The work input for which is Wt compared to the larger will require W for the real compressor. The efficiency of the compressor then can be written as Wt on W. The next picture shows the compressor process in an ideal and actual adiabatic process. The inlet flow at Pi and Ti, the ideal and the real process. We have also PV diagram for compressor. Our final example is that of nozzle efficiency. For nozzle, as discussed in section previously, the purpose of a nozzle is to produce a high velocity flowing stream. Or in terms of energy, a large kinetic energy. At the expense of the fluid pressure. The design variables are the same as for all turbines, PITI and PE, and A as the cross-sectional of the turbine. And nozzle, a nozzle is usually assumed to be adiabatic. Such that the ideal process is an isentropic process. The ideal process is isentropic. from state I to state E. The picture below shows the ideal and actual process in an adiabatic nozzle. With the production of velocity, the VES, the real process is irreversible. With the exit state E having a larger entropy and a smaller exit velocity VE, the efficiency of nozzle nozzles are simple devices with no moving parts. As a result, the nozzle efficiency may be very high, typically in summary. To determine the efficiency of a device that carries out a process, we compare the actual performance to what would be achieved in a related but well-defined ideal process. Summary of general control volume analysis is the next section.